Hello, everyone, and welcome to Growing Investigation 2, which is examining growth patterns. Hopefully, got through Investigation 1 fine and understanding that you could see different patterns, and with different starting values, we had to adjust what exponent we started with. So, as we look here in Investigation 1, you learn to recognize exponential growth patterns. Now you're ready to take a closer look at the tables, graphs, and equations that represent those exponential functions. So we're going to explore this question. How do the starting value and growth factor show up in the table, graph, and equation that represent an exponential function? Now, if we take a look at starting value, if we think back to thinking with mathematical models, sometimes we had a starting value in our equation of y equals mx plus b. Our y-intercept was b, if you'll remember, and that's where we would start when x was 0. So you're going to have to think back on that to be able to help you find a starting point here in all of our investigation 2 problems. So, for example, students at West Junior High wrote two equations to represent the reward in Plan 1 of Problem 1.2 with our peasant hero. Some students wrote r equals 2 to the n minus 1 power, and others wrote r equals 1/2 times 2 to the n power. In both equations, r represented the number of rubas on square n. Again, you could have used x and y or a and b, whatever you wanted to, but again, I want you to be able to identify what your dependent and independent variables are and what they stand for. So I want you to, after I go through these questions, pause the video and be able to answer all of these before proceeding. First, are both equations correct? If so, explain. If not, explain as well. And then what is the value of r in both equations if n equals 1? Once you've calculated that, does this make sense? Why or why not? And what is the y-intercept for the graph of these equations? Do we have one? Sometimes we do, sometimes we don't. How do you determine whether we do or don't? And then do you think there is any value for n that will result in more than one value for r? Okay. So pause the video, answer those questions, and then proceed forward. So in Growing 2.1, our learning targets are I'll be able to recognize exponential growth in verbal descriptions, and I will be able to find the y-intercept and growth factor for an exponential relationship. Those are the two things we want to accomplish here. Our ACE assignments for our investigation 2, starting with 2.1, beginning on page 32, numbers 1 and 4, 15 through 23, 34 through 35. So if we go ahead and turn in our books to page 28, we'll see investigation 2.1, killer plant strikes Lake Victoria, and talking about y-intercepts other than 1 or even 0. Exponential functions occur in many real-life situations. For example, consider this true story. Water hyacinths, which experts say double in area every 5 to 15 days. Okay, they double in area every 5 to 15 days, are expanding across Africa's giant Lake Victoria. The foreign plant has taken over more than 769 square miles of the lake and is growing exponentially. So in Africa, you see the map of Africa here and Lake Victoria here on the southeast side of it. So little progress has been made to reverse the effects of the water hyacinths. Plants like the water hyacinth that grow and spread rapidly can affect native plants and fish. This in turn can affect the livelihood of fishermen. It can also impede rescue operations in case of a water disaster. To understand how such plants grow, we'll look at a similar situation. But to get a better idea of what we're talking about here, let's watch a video about Lake Victoria.
Lake Victoria is the largest body of fresh water in the whole of Africa. Providing a drinking, bathing, and food source, Lake Victoria is essential for humans, birds, hippos, snakes, snails, fish, and many, many more organisms. However, Since the introduction of the invasive South American plant water hyacinth, the surrounding villagers and wildlife have discovered a whole new meaning to the word pollution. No one is sure how the plant reached Africa, but scientists have concluded that even with the chemical, physical, and biological attempts at removing the plant, it has more than tripled in density since 1996. The hyacinth has proved beneficial to some. It has made an ideal hiding ground for venomous snakes such as this ball python, and for many types of birds. These Jesus birds use the hyacinth to walk out across the water, but for most, the repercussions have been nothing but negative. Water hyacinth forms a thick green carpet that prevents the sun from penetrating the water's surface, raises the water temperature, and decreases the oxygen levels. These effects have in return decreased the fish population, which affects not only the fishermen and villagers, but also the birds and other animals that depend on the water stock for food. The increased temperature increases the risk of disease for locals that use the lake as a source of water for drinking and bathing. And the plant is so thick, it has prevented access to the shallow waters on the shore where the hippos feed on the grass and the fishermen can stand and cast their lines. The dense coverings do not remain stationary either. They can drift across the water's surface, thereby taking with them fishing nets and even small boats that are trying to find a path back to shore.
So obviously this is a problem for people that live around Lake Victoria. So we're going to examine a situation very similar to this. And if we look on page 29 of our Growing, Growing, Growing books, we'll see that we're presented with problem 2.1. It says, Ghost Lake is a popular site for fishermen, campers, and boaters. In recent years, a certain water plant has been growing on the lake at an alarming rate. The surface area of Ghost Lake is 25 million square feet. At present, the plant covers 1,000 square feet. Remember, at present, 1,000 square feet of the lake. The Department of Natural Resources estimates that the area covered by the water plant is doubling every month. Okay, doubling every month. So, some things to think about here. First of all, in part A, question 1, they want you to write an equation that represents the growth pattern of the plant. Now, there's a few things we need to think about to come up with this equation. First, is the area of the plant growing exponentially? It says it's doubling every month. Is that exponential growth? And then how do you know that? The initial value is 1,000 square feet, and that's the y-intercept for this relationship. Can you explain why? And again, think back to thinking with mathematical models and our y equals mx plus b equation. So what is our growth factor based on the information you've been given? And based on a possible y-intercept and this growth factor, what information do you need to write an equation? So part A1, we're going to write an equation. A2, explain what information the variables and numbers in your equation represent. And 3, compare this equation to the equations in investigation 1. To give you a little more insight and possibly help you out in this, let's take a look at another short video here.
Recently, Ghost Lake has been experiencing a dramatic change in water plant growth, affecting the entire lake. We'll track the changes that occur in 1 month's time over a period of a few months. As we begin our study, water plants cover a very small portion of the surface of the entire lake. After 1 month, water plants cover twice as much of the surface of the lake as it did before. 1 month later, water plants cover twice as much of the surface of the lake as it did 1 month earlier. Once again, the water plants have doubled in area to cover even more of the surface of the lake.
A little help, please.
This could become a problem.
Could somebody get my sunscreen?
So we've been given a verbal cue there of giving you some directions on how much it's doubling, when it's doubling. Again, does that represent exponential growth? Then part B says make a graph of the equation. I would like you to try to graph it on the calculator. If you don't know how to do that, Google it. Those are TI-84 graphing calculators, so see what you can find out about how to do graphs on those calculators. And then how does this graph compare to the graphs of the exponential functions in Investigation 1? So on the same screen as you've graphed your new equation, I want you to graph y equals 2 to the x power and y equals 3 to the x minus 1 power, all on the same screen so you can see how these graphs differ. And then recall that a function is a relationship between two variables where for each value of the independent variable, there is exactly one corresponding value of the dependent variable. Is the plant growth relationship a function? Now, if you go back to 1.2, you'll look at the vocabulary that describes exponential function. Justify your answer using a table graph or an equation. You can use any one of the three or all three. It's up to you. And then part C, how much of the lake surface will be covered at the end of a year? Think about how often the exponential or how often the plant growth is doubling. And then how many months will it take for the plant to completely cover the surface of the lake? They gave you the size of the lake at the beginning of the problem, so go back and determine that with your equation. I have PEMDAS written here. There's a reason for that. You should know that already. So use that as a clue. So it'd be a good idea if you went ahead and uh, went through these before class started so that when you get together with your teams, you're ready to look at each other's answers and then proceed quickly into your homework. Looking at your homework again for 2.1, beginning on page 32, numbers 1, 4, 15 through 23, and 34 through 35.